are assumptions that we have to follow for a gas to be considered ideal. Okay, so I'm going to give you a couple minutes to write all this down, and then I will hit the main points on it again. Okay. So abbreviate these. You don't have to write them word for word. Put them into your own words to help you conceptualize them better. We're going to talk just a little bit about these principles or these assumptions that have to be true. Okay, the first of which is that in a gas, and in an ideal gas, there's a large number of particles that are far apart. Okay, they are far apart. I guess that's the second bullet here, but far apart relative to each other. So what's that mean, relative to each other? They're far apart relative to each other. Not necessarily. Think about it in terms of our view of distance. Would they be far apart using our measure of distance? No, right? They're going to be like maybe a millionth of a millimeter apart, right? To us, that doesn't seem like very far. Relative to each individual gas particle, those are going to be far apart. Okay, so the gas particles themselves, relative to each other, right? That's why we said relative to each other, they are far apart. Okay, so when we talk about gas molecules or gas particles, they are relative to each other, far apart. They're moving in continuous, rapid, and random motion. Okay, in terms of their random motion, are they moving in a spiral pattern, or are they moving like boomerangs, or what are they doing in straight lines? What do you think? Bouncing around. But do they move in waves as they go? No, they move in straight lines until what happens? Until they hit something, right? Until they make what type of collision? An elastic collision. An elastic collision means they do what? They bounce apart, okay? So all of these things fit together, right? So we've got a large number of particles far apart from each other that are moving in random straight line motion until they hit something. They can hit a wall, they can hit another particle. When they hit that particle, it's going to be a perfectly elastic collision, which sends it bouncing in a different direction, right? Not necessarily right where it came from, but it's moving in a different direction in a straight line motion until it hits something else, okay? The last point here tells us why we have perfectly elastic collisions. Why is there no loss of energy? Why is there no loss of speed here? It's because the attractive forces of these particles, when they get into a close proximity, are ignored. They have no attraction to one another that's pulling them closer or keeping them closer together to slow them down. Even if it's just for a second, does anyone remember what those forces are called? The really short, weak intermolecular forces? Nobody? What did you say? No, okay. They're called van der Waals forces or London dispersion forces. Those are the really small, really short ones, right? Yeah, they are really short. Remember, it happens because of a instantaneous dipole. All right, we're getting out of our realm here a little bit. Okay, so these particles, are those words ringing bells in any way? Yeah. Okay, but they happen because in an ideal gas, we ignore those attractive forces. We're saying there's no force that's going to pull these things closer together or keep them there for any period of time. So as soon as they collide, they're going to bounce right off. Okay, they are perfectly elastic collisions. That's our kind of summation here of kinetic theory. Small particles far apart that bounce off each other. If you can put it in one sentence, that's what it means. Okay? All right. Okay. Look at the connection between the kinetic theory and the gas laws. Okay? So Boyle's law is when we have the connection between what two attributes? Boyle's law is pressure, temperature, volume. What is it? Boyle's law is pressure and volume, right? Boyle means constant temperature, so we have pressure and volume. So the connection between kinetic theory and Boyle's law says when the collisions of molecules cause molecules to slam into the wall of the container, we consider that pressure. Okay, so anytime a gas particle collides with the side of a container, it creates pressure. So as volume increases, molecules have more room, so pressure decreases, right? As the volume increases, they're going to collide into those walls less and less often, which therefore decreases our pressure. Okay, and the relationship between pressure and volume is what type of relationship? A direct or an indirect or an inverse? It's an inverse relationship. As one goes up, the other goes down, right? So that's what we're saying here. The same goes for the reverse of this. If we decrease the volume, what's going to happen to the walls of that container? Yeah, there's going to be more collisions between the gas particles and the walls of the container, which therefore increases our pressure. Okay, do we see that relationship and the connection between kinetic theory? Okay. Charles' law, as temperature increases, that means energy increases, and molecules make a larger container. Okay, so this is one is a little bit tougher for us to understand because we got to keep pressure constant, right? So Charles' law is the relationship between what two attributes? Volume and temperature, right? Charlie Brown's under constant pressure, so Charles' law is constant pressure. So as we increase temperature, which means we input what into the system? Energy in the form of heat, right? As we input energy, we increase the heat. What happens to those gas particles in terms of their velocity? They speed up, right? They start going faster, right? An increase in heat means an increase in kinetic energy, which therefore means an increase in velocity. So the faster they're moving, the more collisions they're going to make, which means the more collisions they're going to make at that wall. Okay? And if we want to keep constant pressure, which is a difficult concept for us to kind of understand, but as we want to keep a constant pressure, the more that we hit into those walls, right, the walls are just going to start to expand. Right? So an increase in temperature means an increase in volume. That's what type of relationship? A direct relationship, okay, a perfect relationship. Okay, Guy-Lussac's law is now the kind of the leftover guy, and he's the relationship between what two attributes? What are the two that are left? Pressure and temperature. Okay. As temperature increases, energy increases, molecules move faster, collide into the wall more often, which is not moving anymore because we have a constant volume. So more temperature means more energy, which means more velocity, which means more collision, which means more pressure. Okay. Ideal gases and what they mean, right? They behave ideally. In terms of an ideal gas, any gas can behave ideally. Okay, we hope that every gas behaves ideally. That's how we do all of our problems, assuming that all gases behave ideally. Is that really the case? Not so much. Okay, so now we're going to look at the little differences between ideal gases and real gases, how they perform in everyday life. Okay. So ideal gas law is not a perfect description of a real gas when the pressure is high or the temperature is not at an extreme. Okay, so if our pressure is really, really high and our temperature is not extremely high or extremely low, real gases behave a little bit differently, okay, than the ideal gas law really shows us. Okay, so when we reach a high pressure in the system, we expect our gas molecules to be really, really close together, right? If we have high pressure, that means they're bouncing back and forth a lot. We expect them to be close together. And we get to really low temperatures, we see that our attractive forces between these objects are no longer negligible. What happens when we have high pressure and low temperature? Give me the characteristics of those gas molecules at that point. Okay, low temperature and high pressure. How are those gas particles behaving? What did you say? Yeah, they're moving slowly. And when we're at high pressure, what does that mean in terms of their proximity? They're close together, right? So they're moving slowly now, and they're closer together. They're kind of sluggish. So now those attractive forces are not necessarily so negligible. They're not moving as fast. They're not making these elastic collisions. Those attractive forces get to be a little bit more important. Okay, this is because of reduced energy. We just talked about that. We described that in terms of the behavior of those particles, right? They're moving slow and they're close together, so they might as well just hang out, right? That's their thought process. Okay. Real gases and ideal gases behave really similarly, except for, okay, quoted from your book, except for as long as the pressure is not too high and as long as the temperature is far from the liquefaction point. Okay, far from the liquefaction point. Okay, so as we can see here, this temperature and pressure relationship should be direct, right? If one goes up, the other goes up. We see both of these graphs are temperature versus pressure. Okay, and the general trend for this graph on the right is upward and to the right. Okay, it makes that general trend. But this splits it into looking at the phases of water. This is a phase diagram of water under certain pressure and temperature conditions. Okay, this gives us a really generic kind of path, but this breaks it down even further, and this is what we're going to look at. Okay, is this ringing a bell from Honors Chem? Yeah. Okay, good. All right, so ideal versus real tells us this phase diagram between liquid, solid, and gases of water. We're going to study the water phase diagram because it's the simplest and it's the most used. But every compound has its own phase diagram that tells us under pressure and temperature conditions what phase is it in at this point. Okay. All right, so you want to go ahead and sketch this down. Go ahead and do that. I'm not going to give you a printout of it this time. Just go ahead and sketch it. It doesn't have to be perfect. And then we're going to go over what all these points mean. We'll see what you remember from that. Okay, so the triple point here is where all those curves come together and they meet. So the conditions for water's triple point is 273.2 Kelvin with really low pressure, 0.006 atmospheres of pressure, right? We're low temps, just above freezing, okay? Low temps, and really extremely low pressure. Okay, let me switch a point. What's it mean to be at equilibrium? You should know this one. Being at equilibrium, does that mean that everything stops? No, it does not mean that everything stops. It means that the forward and the backward processes are happening simultaneously. Okay, so as we see this triple point, we see the transition from liquid to gas and gas to solid and solid to liquid, right? They're all happening simultaneously within that same system. Okay, so once we reach an equilibrium, it doesn't mean that everything just stops changing. It means that the changes are happening at the same time. Okay? Does that make sense? Okay. So our critical point is labeled E. Okay, critical point is way up here, E. It says the point at which the substance can no longer exist as a gaseous state. Okay, and so on your chart here, it's labeled at 647 and 218. Those are rounded, but they're really pretty close to what they should be. Okay, what happens after the critical point? What happens? Anybody know what happens after the critical point? Curve A is an equilibrium curve between solid and gas. Curve B, what do we think probably means? Between what? Liquid and solid, right? You can tell right from your graph. They're all equilibrium curves. So any conditions that meet along that line are going to cause an equilibrium. Okay, so for curve B, it's between solid and liquid. That means curve C is probably an equilibrium curve between what? Liquid and gas. Okay, or vapor. For water specifically, it's called vapor, but most is going to be gas. Okay, so that is an equilibrium curve. Any conditions that meet along that line cause an equilibrium. That's what I want you to remember. Any conditions that meet along that line will cause an equilibrium. Okay, but each compound has its own critical temperature that it reaches, that it no longer can be that gaseous state anymore. Okay. And the last little thing I want you to look at is the difference between vapor and gas, because I think sometimes those terms are used interchangeably, and there is a slight change between those two. Okay, so gas is a gaseous state of a molecule when the temperature is above its critical temperature, and a vapor is when the temperature is below its critical temperature. Okay, so we might be above the critical temperature, but we're not above the critical pressure, right? So we're still in that gas state. But there is a difference between gas and vapor, and I didn't know that difference for a long time. But there is a slight difference. Okay, so if you go back to look at your diagram, you can see like the examples of when that might be the case, right? We might be above the critical temperature, but our pressure is still at 1 atmosphere, right? So that's going to keep us at a gaseous state. But if we hit that really, really hot, if we're hitting a high pressure but a low temperature, we're not above our critical temperature, then we're still considered that vaporous state. Okay, so there's a slight difference between those two.